Okay, MMI711 sequence models in multimedia. This is the third week. We have been talking about what sequence are, and we've talked about the vanilla RNN, which is the regular recurrent neural network with a feedback connection, a simple feedback connection, and an output layer if it is required. But we haven't talked about how they are trained, because there are a lot of to talk about when it comes to training recurrent neural networks, guys. So let me begin. We have so many things to talk about. Okay, so we are going to talk about training RNNs. We are going to talk about how backpropagation works when you're training recurrent neural networks. We're going to talk about how you can modify backpropagation procedure when you're training recurrent neural networks. Then our discussions will lead us to the famous vanishing gradient problem. Vanishing gradient problem is a problem that inhibits us to properly train recurrent neural networks. Actually, there's a solution, and the solution is the next week's solution, which is next week's discussion, which is LSTMs, and we are going to discuss further subjects. Let us begin. So, remember, we have unrolled the RNN in time, which means when you're feeding sequences to the RNN, so your input to the RNN is a sequence of vectors, which have the same size. So let this be the vector, for example. Let me find the cursor. Sorry, let me find the cursor here. So this is xt0, xt1 until xts. Remember, s being the variable input sequence length was something wrong. I forgot to change in my slides. Since it starts from xt0 and ends at xts, this should have been s plus 1 being the variable input sequence length. So minor typo, but never mind. And according to our input-output model, we have designed a system. Remember, this was a many-to-one problem. So many-to-one. This is a many-to-one. How do I know that? Because I have many different types of inputs, and I'm only getting the final output and ignoring the intermediate outputs. That's why I call it many-to-one. Just an example. For example, in this many-to-one type again, RNN can be thought of an S plus 1 layered FNN. So let me just write those. So why don't I write those? I forgot to change the slides. So at least I can just write those on the video. This should have been S plus 1, and this should have been 1. Okay, so no worries. We can okay, we would like to train them. What are we going to do? We are going to apply backpropagation, because backpropagation is an efficient, computationally and memory-wise, efficient way of training these graphical models. So I'm going to apply backpropagation to this model, because when I unroll this in time, it becomes a linear graph model. And since it looks like a computational graph, I can apply backpropagation to any type of computational graph I want to. So how it is done? So I'll have to remind you very briefly what backpropagation was. I'm sure you know what it is, since you have taken an introductory level course on deep learning. It is backpropagating the gradient of loss, the loss function, with respect to the weights of the network. And you're doing this to each layer separately. First, you're finding the partial derivative of the loss with respect to the weights at this layer. Then you backpropagate using the chain rule of derivation. Then you find the loss, partial derivative of the loss with respect to the weights of this layer. And you go back in the computational graph, in your network. That's simply what backpropagation was. Backpropagation is a very famous idea, and it's been used in these kind of networks for a while. You know, remember, we have gone over the history of this stuff, and backpropagation was found around somewhere in the 70s, so 50 years old. So in this many-to-one corrected example, is a loss function, and you're backpropagating the loss in this direction, because when you unroll an RNN in time, it simply becomes an S plus 1 layered, in this example, linear graph. And at this point, if you have difficulty in remembering what backpropagation was, you have some options. You can go back to your notes in your previous course, the prerequisite course. I'm sure there are a lot of sufficient notes in your previous lectures, lecture notes. Or a simpler solution is, you know, Stanford is a fantastic course on deep learning, introductory level deep learning, and week 4 is dedicated to backpropagation, and Justin just talks about it in a very kind and gentle manner. So just watch this one. But I'm skipping right now. I'm assuming that you know what backpropagation is briefly is. So it was backpropagating the derivative of loss with respect to the weights, this guy, in the graph in the backward manner. And in order to update the weights at each iteration, an iteration is passing a number of batches of inputs on the graph, you apply the basic rule of gradient descent. This is the basic rule of gradient descent. For a layer, you have weights. So the new weights, when they're updated, will be the old weights minus a learning rate, which this guy is positive because this gradient should be subtracted from the old weights. That's the rule of gradient descent. So positive learning rate times the gradient of loss with respect to the weights of that layer. Simply, you are looking for the correct weights, assuming that the function is a convex function in optimization terms. It is not a convex function, but in the end, in deep learning, in backpropagation and in training, what you do is you are looking for a local minima where you will overfit to a good accuracy over a large data set. That's what you do. That's the general training rule of all deep learning systems. And it is the same here. What we are going to be doing is we are going to be backpropagating the loss over this unrolled in time representation. So actually, when you're backpropagating the loss in a computational graph, which is hypothetically created by unrolling the RNN in time, actually it has a newer name, which is called backpropagation, not through layers, but since this sequence dimension is usually called the time dimension, it is called backpropagation in time. So I'm going to get there. This is called backpropagation in time. I've been saying for 10 minutes now that this backpropagation is no different than the backpropagation of a linear in a linear layer. Is it so? I mean, is it so? I'm asking you, is it so? Is it exactly the same as backpropagating in LXNet, for example? Because LXNet is something like that. It is not directed acyclic graph. It is a serial graph, just like this. There are layers, and there are different types of layers, but in the end, you have a serial connected network. I'm talking about LXNet. It could be VGG or other serial connected networks. So you're backpropagating layers. Is it exactly the same? Is there a difference? Any ideas? Anybody would like to make a comment? No comment? Actually, there's a very important difference, guys. In LXNet, when you are backpropagating the errors through each layer, this update is applied to each layer weights. And when you're applying this update, gradient descent update, using the backpropagated partial derivative of loss with respect to the weights at that layer, you're updating only these weights, which makes sense. However, when you unroll an RNN in time, what you're doing is you're updating the same weights everywhere, because actually we don't have this many layers. We have hypothetical representation like this. The weights are shared in this network. So unlike other previously trained serial networks, an RNN unrolled in time share at all its layers share the weights. So at each layer, you are actually updating the same weights for all layers. So remember that this is not actually S+1 layered FFN, fit for neural network. It's a single layer which calls onto itself. This representation unrolled in time is actually just a representation. So what you do when you update any of the weights, you're updating all of the weights, which is in a way good, but which is in a way bad. Why bad? We are going to be discussing this today thoroughly. But the situation is when you have a very long sequence, you're updating, for example, S is very large. And in that case, you're updating it like S+1 times. And as you update it, for example, S is 100, then you're updating the weights for 101 times. After the update 50, you already gone over the first update like 49 times. So it is like you're updating the weights so many times, you're going over the first update of your cells. So it is forgetting the update rules. So as long as the sequence gets longer, this type of a network is, I mean, expectedly will be difficult to, it will be difficult to train. That's the problem. Okay, we're going to talk about these problems. We are trying to understand the problem right now. So the weights to be updated at each layer are the same weights. We know this now. In this many-to-one example, we are updating the same weights S+1 times. Are the weights, in other words, overwritten S times? Yes, but not necessarily. If we apply the entire sequence, that will be so. We don't have to apply the entire sequence. So this is called backpropagation through time. Very simple, as if you've checked Coursera course from Andrew Ng, backpropagation through time. It sounds so scientific, science fiction. Yeah, you're backpropagating through time. And if you're going to make it full, it's going to take as the sequence length. Very good. Why did I say not necessarily? Because you don't have to. You could just take a part of the sequence and just apply it for that part only. Okay, let's go over backpropagation through time before coming to that part where we partially apply the sequence for training, because that will be another dimension of backpropagation through time. Okay, in an RNN, what we do is called backpropagation through time. Abbreviate this BPTT. I'm going to call this BPTT sometimes. By time, we don't have to necessarily mean time. It could be a video, then it's time. But it could be text, then it's not time. It's the sequence dimension in more general. The pseudocode for BPTT can be written as, you do the forward run for an input-output pair, but not for an input-out pair. Okay, for an input-out pair. Then in the backward run, you unroll the network and calculate and accumulate the errors across each time step. And when you're updating at each layer, you update the weights using the accumulated error for all layers. That's the beauty of backpropagation through time. Maybe we should have put this in the slide like this, for all layers at each step. Good. And we repeat this for each batch, and for each batch it is iteration. And when all batches in the training set are repeated, it's an epoch. And when you repeat the epoch, it's multiple epochs. You know what backpropagation is. You have trained the system in your life, so you know what I'm talking about. Okay, good. This is backpropagation time, and the update procedure is just gradient descent in our case. I mean, not necessarily gradient descent, of course. I mean, you're using Adam or you're using momentum, whatever. But at the heart of the update mechanism, you have this guy. There are a lot of elements you can add to this, the momentum or the adaptive learning rates, Adam. You know those because you have taken an introductory level course. If you don't, just go over the solvers, different solvers. What is Adam? What is momentum? Just check those, okay? There are two main problems with backpropagation through time. I tried to touch those in a couple of minutes ago, but I'm going to just go over the slides and make them clearer. as the sequence gets longer, if there are multiple outputs, as in many-to-many case, the derivative is calculated with respect to a sum of many different losses obtained from different elements of sequences. So different types of losses will go over the weights. Well, this is not a problem, but this could make the training a bit difficult because you're updating these weights using this loss and this loss, but you're updating these weights using only this loss. And actually they are the same weights. Okay, let's for a moment assume that the dynamic system to be trained, the weights space, can handle this because you have the capacity, or RNN have the capacity to learn the universe. Remember, RNNs are, I mean, universal sequence approximators. Good. More important problem is the number of derivatives required for a single update weight can cause weights to vanish or explode when you're back propagating. So, okay, you're updating over and over again, and you're writing over them. But when you're writing over them, maybe in the first dot that I mentioned, you're overwriting the weights, but maybe the weights are evolving that way, and maybe the system can handle that. But the more important problem is people have realized, working on recurrent neural networks in the 80s, is as this sequence gets longer, the gradient starts to vanish or explode, usually vanish because of the type of the activation function. That was what they practically observed. And as the gradients vanish, and after some layers during the backpropagation, imagine there are some layers here, 10 layers, and this is the 5th layer, and gradient dies at the 5th layer. You cannot do updates using these inputs and these outputs if you have any. So vanishing gradients was a problem that limited the capability of backpropagation through time for recurrent neural networks. So let's, okay, what was vanishing gradients? I'll get back there. I'm going to get there, so don't worry about it. Just mentioning right now. So what we can do is, remember I told you, when you unroll this graph in time, it's going to be an S+1 length sequence. If I'm starting from xt0 to xts, it will be an S+1 serial graph. I don't have to necessarily use all the input sequence for training. I could just make little pieces of sequences and subsequences from the entire sequence. Maybe overlapping, maybe not overlapping. This is my design. I can apply them to backpropagation separately, like batches. So instead of batches of the training sets, I'm also having another combination of batches using the subsequences of the sequence. This will limit the effective size of the network while I'm training it. Well, this will help me because I know that as long as the sequence gets larger, I'm having problems, I'm experiencing problems. This is called the truncated backpropagation through time. As the name implies, you are truncating the input sequence and creating some subsequences. So truncated backpropagation through time is a modified version of the backpropagation through time algorithm for recurrent neural networks, where the update steps are splitted, truncated. How? There are different strategies. I cannot tell you that this is the usually correct way of training RNNs. I mean, this is a fundamentally important method. You may want to apply it, but before I tell you what truncated backpropagation is, because it's important that you theoretically understand what truncated backpropagation, I must tell you that this problem of recurrent neural networks being trained the problem of the difficulty of training recurrent neural networks was not solved by truncating the backpropagation through time algorithm. It was an early idea that researchers thought that might work, but that was not the case. They found different solutions. However, still, backpropagation through time may be useful for some simple problems. We'll get there. Okay. So I'm going to start discussing how truncated backpropagation should work. And I'm going to start with a simple strategy for a many-to-one architecture. So there are different strategies to apply truncated backpropagation through time, because it's like a handcrafted design. You're going to split the input sequence to pieces, but how many pieces? Are they overlapping? What is the length? Blah, blah, etc. Let's analyze a many-to-one problem with a single loss at the end. Because it's a many-to-one, I'll have a single loss, which makes my gradient flow simpler. That's why I'm choosing this model for the sake of simplicity. Let's say the problem we define is sentence grammar detection. I always define the problem first, guys, because without the problem definition, it's usually very difficult to understand what we are working on. So this is a many-to-one problem. The many input is the sentence, the words. Somehow the words are vectorized. It's called embedding. We are going to get there in the following weeks. And fed to the RNN. And I'm checking the last output. For example, the sentence, there will be words, and there will be the dot. And my network will understand when the dot comes, it should output the correct output because I'm going to be checking it. Because during training, I'm going to get the loss, only the loss, after the dot is provided, and backpropagate that loss through the sentence, the sequence. So input is English, sentence in English, whatever. Output, if that sentence is grammatically correct or incorrect. Actually, you have this in Google. You have this in Word for many years. MS Word was not using a sequence model previously, but it is now. So it is, this is a grammatically correct sentences, the dot. So I have 1, 2, 3, 4, 5, 6, and the dot, 7 elements in the sequence. Okay, so I'm feeling, why am I doing always these? I'm sorry, this time it is not 8, it's 7. About the sequence length, I have always errors. Let me just write it. Why am I doing these errors? Because it's something very difficult to prepare slides, and you always have errors. So Ali Hoca will understand. And whatever you work on, after years and years, you have these errors. Okay, anyway, I'm feeding a 7 long sequence to the RNN. Good. When unrolled in sequence time dimension, I will have 7 layers connected if I am to apply a full backpropagation through time, which I'm not going to do because this is an example of truncated backpropagation time. So how am I going to apply it? How am I going to apply it? First, regular backpropagation through time. I've got 7 layers. I have the loss at the end. I apply backpropagation for each sentence. And as the sentence changes in the training set, my backpropagation size will also change. I'll be backpropagating 7 times for this sentence. For another sentence which has 9 words plus the dot, 10, I'll be backpropagating it 10 times. So the weights will be updated 10 times for a 9-word sentence plus the dot. Simply that is it. If it is a truncated backpropagation through time, I have some hyperparameters. Hyperparameter being the splitted sequences that I'm going to be using for backpropagation. Let's define K. Actually, the split will be different for forward and backward passes separately, but I'm going to assume that I'm using the same split size for forward and backward passes. What I meant, I'll try to make clear. So I first get only a 3-sized sequence from the subsequence from the sentence. So this is a 3-element sequence. I feed it to my unrolled in time representation. I have some activations. When I'm backpropagating the loss, I use these activations and the updated weights to update the system. Since this entire sentence in the training set is grammatically correct, I'm assuming that all the splitted parts are also grammatically correct. So for this example, this will be a true example, which is kind of confusing because this is actually on its own is not a grammatically correct sentence. So at this point, I realized that applying a truncated backpropagation for this example may not be a very good idea, but still it may be a good idea because I'll be training this network not only for this subsequence, I'll be feeding other overlapping subsequences as well. Just like this is a grammatically. So still, I have some doubts about it because I'm feeding subsequences, and how can somebody or a machine understand if the entire sentence is correct when you feed the subsequences of that sentence? So it's like a trade-off, guys. I'll have to trade off my problem definition with the trainability of the system if I had that problem. Because when I fed very long sequences, I couldn't train the system. I truncated the inputs, then the problem definition did not work for me. What I'm trying to say is truncated backpropagation in time can technically be applied to any sequence problem. However, that may also change your problem definition, and maybe it is not the right way to do it. Let me continue with the slide. So we are practically truncated the backpropagation through time sequence length by cropping the input to smaller pieces, subsequences. Is a good idea for a problem. What are the pros and cons? I've already started discussing it, but let's discuss in the slides. For this problem, the pros were the system became more trainable because for very large sentences, maybe I was not able to train it because practice tells me that I'm not able to train it. We're going to cover a very simple example today in live code, so you're going to see it yourself. So is this a good idea? What are the cons? This is the pro. This was the pro. What is the con? Well, I'm feeding subsequences, and the system can only understand if the subsequence is part of a grammatically correct sentence. However, maybe another part of the sentence was grammatically incorrect. In this case, it's a bit confusing for the system to train. So I wouldn't expect very large accuracies for a system like this. Okay, let me go. Let me apply it to another problem. Okay, for example, a speech-to-text problem. In a speech-to-text problem, at the input you have signals, quantized values. And you are feeding quantized values to the network, and you're getting words, for example. Actually, this is a simplified representation. This is not what happens in speech-to-text. For the sake of simplicity, I've simplified this figure like this. What happens is, this is not the words actually, a thing called phonemes. A phoneme is a piece of sound that you make when you're speaking a language. In Turkish language, syllables and phonemes are the same because the definition of syllable, hece in Turkish, is a single piece of sound that you make. However, for other languages, this is not the case. Syllables, hyphenation, and phonemes do not match for English language. So usually when you're doing speech to text in real world, this machine first translates pieces of sound to phonemes, then another machine, a decoder kind of thing, combines those phonemes to find the words. However, again, to make this figure simpler, I've put it as if each piece of word sound is coming one by one. So this is sentence. That's not the case in real world. But to make it simpler, because what we're trying to understand right now is not the model for a speech-to-text problem, but backpropagation through time. So when you apply backpropagation through time to a many-to-many problem, you are feeding the error in this unrolled in time graph in different losses, right? So I just like it. Actually, this is more like fixed length sound pieces, sample vectors being fed as a sequence, not like this, whatever. Okay, so total sum of backpropagated through time is used. You sum the losses, total sum is used while you're calculating a partial derivative. So it's a bit more complicated, but it's not much complicated. It's simple because in the chain rule of derivation, you have linearity. You can add different sources of losses. And in a computational graph, you just add them, nothing else. And you update the weights at each layer, backpropagate. Do I need an RNN for speech to text? The first question, why did I need this? Do I need an RNN? Because why don't I do this using a feed-forward neural network? Because when I have a feed-forward neural network, I have a sound, I'll find the matching word. Do I need it? Any ideas? No answers. Do I need an RNN for a speech-to-text problem? Because a convolutional neural network can also do it. Why would I use an RNN for speech-to-text? No answers.
Maybe because of the data structure. No.
Can you give me an example about the data structure?
I mean, we know that the text data is kind of sequential data. That means it has a relationship inside it.
Okay, what can you give a solid example? Yes, you're right. Definitely, that's the answer. But there are some solid examples for that. For example, can you think of one?
Let me think.
Okay. For example, can homophones be an example? Homophone is a word having the same sound but have different meanings. So they have same sound, they are written differently, and they have different meanings. So how will I understand which word is it? According to the sequence, right? Homophone. Eş sesliler. But your friend was right. The structure of the word and structure of the sentences may mean something. When we are speaking to people, they use homophones, homophone words, eş sesli kelimeler, and we understand them because we understand the sequence of the sentence. So yes, a recurrent model is needed for speech-to-text to handle things like homophones. Good. Is truncated backpropagation a good idea for speech-to-text? Because in the previous example, we have seen that it was not. I mean, because a part of the sentence may be correct, while another part of the sentence may not be correct. So it was not a very good idea. What is the case for speech-to-text? Would anybody want to make a comment? Okay, probably yes. I'm not saying yes. Because just like I said, when you truncate the backpropagation, you're actually weakening the ability of that RNN as a sequence model because you're limiting the sequence size. Because you just make it very small, it will be like a convolutional network because a convolutional network will be just trained with only single examples, one by one. So when you make it a unit length, like a single phoneme, it will be like a convolutional network. As you make it bigger, it is hard to train. So there's a trade-off in between. For example, imagine I'm using fixed length sequences while training, truncating the backpropagation, like 3 seconds. So 3 seconds, I'm training it with 3-second pieces. So the relations within that 3 seconds will be learned, okay? In other words, if you can understand the homophone in 3 seconds, then you'll be able to learn it. It's that simple. Probably yes. So this was about truncation in time. So let me. So there exist different designs to apply. Before that, before I continue this slide, let me ask you: do you have any questions about applying truncated backpropagation to different problems and their pros and cons for these two problems, grammar detection and speech to text? Well, and if you have any questions about why it is a good idea, what is not a good idea to apply truncated backpropagation, and what we are trying to solve. Any questions? Okay, I guess not. Okay, so just like I told you, applying truncated backpropagation in time is a handcrafted design. It's a handcrafted design because how long the sequence will be, we don't know. It depends on the problem. Maybe it's going to work for a sequence limit, but it won't work when you make it smaller or larger. Because if you make it larger, it will be difficult to train the system. If you make it smaller, it will lose its ability as a recurrent model. And when it is not a recurrent model, it won't be able to solve a recurrent problem, sequence problem. And also, you can make another design choice while you're making the backpropagation through time of forward and backward passes. Because when you're forward passing, you're applying sequences. the number of truncated passes you apply to forward and backward cases can also be different. For example, you select 4 sequences for the forward case, so the forward case will be updated 4 times, but the back propagation will be done only 3 times. You can choose it because you're updating the same way. So the case will not be like you have left a layer unchanged. You're always changing the same layer. So during back propagation, you know, during training, we have to do a forward pass, then the backward pass. The truncation numbers for the forward pass and the backward pass may also change, which may make sense for the different type of problems. I don't know. So truncated back propagation through time is highly a handcrafted design of training recurrent neural networks. Okay, how many elements to feed in the forward run, how many elements to feed in the backward run? These are design choices. So an example, I'm feeding 4 elements in the forward run, but I'm only using 3 elements for training. That's why I'm using this loss and updating only 3 times. So K1 is 4, K2 is 3. K1 is the sequence length I use in forward, and K2 is the sequence length I used in backward run. Well, these are some choices for training. It doesn't have to necessarily mean something. With truncated back propagation in time, which is actually an idea which is not used anymore because we have much better models that allow recurrent or non-recurrent sequence models to handle very long sequences. We have other solutions for that, but this was one of the earlier solutions, and understanding this solution actually will help us to understand what is the problem with training recurrent neural networks actually is. Okay, so another case where K1, a general case where K1 is larger than K2, so you're applying some inputs K1, but you are using only K2 as the total loss. Good. Will this help with homophones? For this speech-to-text example, we have talked about this actually. It may. The answer is it may. If the dependencies that makes us understand what that homophone word exactly is within the truncated distance, 3-4 word distance in this example, then it will. I mean, if just by checking that part of the sentence, you can understand what homophone word is actually provided in the sentence, then you can. But if the dependency of that word within the sentence is longer, it may not. So at this point, I'm making a definition like dependency. I make this definition such that the relation of that word to the entire sentence or to another word in that sentence, to somewhere in that sentence, it's to the entire sequence. These dependencies, if those relations are considered in sequence dimension, they are called dependencies. So you will hear me saying short-term dependency or long-term dependency. Short-term dependency will mean that a sequence element's relation to its nearby neighbors in the sequence. Long-term dependency will mean an element in the sequence being related to another part of the sequence which is farther away in the sequence dimension. Okay? So it is like there's a sentence, you exactly try to understand what the first word means, and you cannot understand it until you get the last word. And if the sentence is very long, that would be an example for a long-term dependency. We'll be using this dependency definition a lot because this dependency definition will lead us to the idea of attention, because that relation generalized in the network will lead us to the idea of attention, guys. So you know what this dependency is. Sequence dependency. The interrelations within a sequence determines the context of the sequence. Basic definition. Anybody would understand this because it's the only thing that makes sense about sequences. Hence, the dependency is the main focus of training, learning in a sequence models. That's what we are trying to learn. That's the difference of a sequence model compared to an FFN, feed-forward model. Because they cannot learn the sequences, because they cannot learn dependencies. Homophones was an example of a dependency in a sentence. To understand what the real word was, I mean, in the set of homophones, you use the dependency in the sequence. Then, just like I said, in the following weeks, this dependency concept will be generalized to the concept of attention. Good. Now, let me get back to the training part where we try to understand what this generalization of training is. How to implement the loss depends on the output type. Just like I told you, if you have many outputs, then the loss will be calculated differently. The loss will be single if there's single output. If there are multiple output experiments, the losses will be added. Summation of various outputs. Good. Let's take a closer look to what happens during backward pass. Okay, in the backward pass, if there's single loss, you just backpropagate the loss one by one. And this guy is updated continuously. Well, what happens when we update it continuously, guys? We use this derivation rule. So it is like you have an activation here. And during backpropagation, this partial derivative is backpropagated, okay? This is what comes from the previous, the forward layer during backpropagation. So I got it here, okay? I got it here. So what I need is to backpropagate it to here so that backpropagation can continue, okay? So what I need is this loss with respect to this guy. They are the same thing. So I have this, I need this. What I have to calculate is this. So this is the output here, and this is the input here. So this is like the input x, the input x, and this is the output y. So if this was a function like this, I would have written it this way, x being this guy. So this would make this box f, right? So to backpropagate, as you all know, what I have to calculate is the derivative of f with respect to the input. Very simple. Okay, okay, very good, very good. Let's try to do it and see what happens. Remember, in a simple recurrent neural network and vanilla network, which is, I mean, we're not going to be using recurrent neural networks, vanilla recurrent neural networks, but as you all know, any type of neural networks, artificial neural networks, multilayer perceptrons, practically the same thing, or convolutional neural networks, you have this architecture. You have the input, being multiplied with the weight plus a bias. Okay, so this is the case. So x is a here, because for this example, I'm trying to get the derivative of this. If you get the derivative of this function, I said f in the previous example, but in this slide is g, so f and g, the same thing here. If I get the derivative of this guy, I mean, according to the rules of calculus, this will be the derivative of this function, because this g is a nonlinear function, whatever derivative it has. If it's a tangent, hyperbolic tangent function, it will have an according derivative, times the weights going outside, because there is a linear multiplication here. Omega times the w times x plus b. Because if you take the derivative of this function with respect to x, according to the rules of calculus, it will take the derivative of inside first, then the outside. Rule of derivation in calculus. So this guy will get outside. And this guy is the weights. So for one layer, you do this. And it will be backpropagated. Right now, we have this here. So if I have this here, just remember the previous function. This weights will be, as a multiplier, passed to the previous one. I'm going to be doing this many times for the sequence. So next time I do it, it will have a square. Next time I do it, it will just continue being multiplied with itself. So while you're back propagating, actually you are taking whatever this thing is. It is most probably not making it larger, guys. I'm going to get to this part as well. This guy is being multiplied with itself. As the sequence gets longer, this exponent here will grow, right? So remember gradient flow from the previous years in the prerequisite introductory level course, because I discuss it, I'm sure. The course you have taken also discussed this. This activation function is usually a 10H. You remember what a 10H is? 10H looks like something like this. Let me draw 10H. 10H is something like this. So let me just draw it like this. The derivative of 10H is, as you can see, at some point it is 0. So it will be something like this, guys. I'm drawing it very bad, but D is derivative of G. And this guy is G. This is for 10H. So for most part of the problem, these are zeros, as you can see. These are zeros. These are zeros. So according to the value of the inside multiplication, this is most probably 0. It is not 0 for a small part. So this is probably zeros, mainly zeros. And this guy is, if this is 10H, this is second, hyperbolic second, this is guy. It reaches to 0 because I'll be multiplying. If this one is not 0, in the other pass, if it is 0, it's going to be 0 as in any case. I mean, I'm applying the back propagation to full back propagation in how many times? The sequence length. If any of them had a 0 gradient, it would die. One of them only. So it reaches 0 because the probability of this guy being 0, this multiplication being 0, gets larger and larger as the sequence length is larger. So this is one side of it. And there is the other side. What is it? The other part, remember? This was one part of it, and this was the other part. This guy being exponents, having an exponent. So if the sequence length is S, I'm having this value. Remember from linear algebra, very simply, if you have a single value decomposition of this guy, which is larger than 1, then you make this exponent, it will explode. If it is smaller than 1, it is going to vanish. And remember how we initialize weights. We usually initialize weights using numbers smaller than 1 in nearly all of the initialization techniques. So that's why it's going to be vanishing. So this guy is vanishing as the sequence gets larger. This is probably going to 0 when the sequence gets larger. Then when the sequence gets larger, this partial derivative that's back-propagated through time will be reaching 0. That's the problem of vanishing gradients, guys. So vanishing gradients problem is, as the depth of the computational graph gets larger and larger, because of the nature of the network, the gradients starts to die. And this problem is severe for recurrent neural networks, because in recurrent neural networks, the weights are the same weights. So if the weights are the same weights, we are left with this backpropagation function here. And either this part and this part is running to 0. So at this point, at some point, when S is above a threshold, it will die. And for your system to train a sequence larger than a length will be impossible. This is called the vanishing gradient problem in recurrent neural networks. I'm going to delve into this subject deep in the next hour before I give a break. If you have any questions about these slides, because it was a bit not tough, but deep Please ask me now.